Okay, the second problem on the quiz. We said that I accelerate upward at 5 meters per second squared, and I do that through a distance of 0.4 meters. So, I crouch down here, and I use more strength than this old man has, and I come springing up, and I rise through a distance of 4 meters while accelerating at 5 meters per second squared from rest. Obviously, if I start down here, I'm at rest. Come up 40 centimeters, 0.4 meters at this acceleration. So how fast am I moving at that point? Because if I do this, then at the point where I've gone through the 4.4 meters, my feet are going to leave the ground, and I'm going to rise a certain distance. Well, we want to find out how fast I'm going at the end of this time. We can use the fourth equation of motion. Okay, and there's no way we can reason this out. We can't combine acceleration with displacement. That's not related by any of the definitions. We can't combine acceleration with initial velocity. That's not related by any definition. And delta S, our displacement, and our initial velocity are not related by any definition. So we go to the equations, and we use the fourth equation, noting that we know V naught, we know A, and we know delta S. We circle those quantities, and we solve for the quantity that's not circled, which is VF. And the solution is very simple. If VF squared equals this, then VF is either plus or minus this. So we plug in our numbers. V naught is 0, so V naught squared is 0 meters squared per second squared. 2A delta S is 2 times the acceleration, 5 meters per second squared, times the 0.4 meter delta S. We multiply this out, and we get 2 times 5 is 10 times 0.4 is 4. Meters over second squared multiplied by meters is meters squared over second squared. And we take the square root, we get 2 meters per second, again with the plus or the minus. We discard the negative quantity because obviously in this situation nothing is moving down. If we assume up to be the positive direction, then no negative solution is going to have any validity, at least not on this interval. So we discard the irrelevant solution, but we use the other solution, the VF equals plus 2 meters per second. So we conclude that I attain a velocity of 2 meters per second. Now, we could have worked this out. I'm sorry, we can proceed to work out the rest without employing the equations, or we could employ the equations. We now have 4 quantities. Any equation that has only 3 of those quantities can be solved for the one that we don't have. Well, the one quantity we don't have is our delta T. I was looking at the wrong thing here. Okay, and I wasn't seeing what I wanted to see. Okay, I was looking at A, and I knew we had A, so okay, well, we're trying to find delta T. And to find delta T, we would use A equals delta V over delta T, which is a result of our definition of acceleration. Average rate of change of velocity with respect to clock time is change in velocity divided by change in clock time. We solve this relationship that we get from our basic definition for delta T. And we get delta T equals delta V over A. Turns out then that we're going to divide our delta V by our 5 meters per second squared, but at this point we don't have our delta V. So we come back here and say, okay, we're going to do a direct reasoning. We know VF and we know V naught. We found VF. Now that's new. We can combine that with V naught to get our V bar, our average velocity 1 meter per second, our delta V, change in velocity of 2 meters per second. Okay, so we take the delta V and the A, the change in velocity divided by the acceleration, getting the change in velocity here, and we determine our time interval to be 0.4 seconds. There's something extraneous down here. I lost track of what I was trying to find, and I was thinking back to the last problem, and I you can kind of ignore what's crossed out down here. I will note that what's crossed out as a calculation shows delta S is 0.2 meters. When we know darn well delta S is 0.4 meters, so there's clearly something wrong here. I multiplied V bar by delta T, but I used a delta T from a previous problem, the 0.2 seconds we had in the preceding problem, which is how I got this. Had I used the correct 0.4 seconds that we have here, then I would have gotten the 0.4 meters that I already knew. And there wouldn't have been any point in doing that except to check the consistency of my calculation for delta T. Okay, well, we go on, and I'm not going to do a separate video for number 3.